So this is our continuing discussion of Cavailles and Lotman's mathematical thought, standing in for the Simondon reading group. So we've read in the last two sessions, we read their presentations and the first part of the discussion after their presentations, and we'll continue with the discussion today. And hopefully, I think we should be able to finish the rest of the discussion today. So some of the discussion that we saw last time, it was mostly, I think everyone who comments in the part we read last time is a mathematician, and they all make this comment about how, I'm a mathematician and I didn't really follow all of the philosophy and all of the philosophical nuances of the presentation. So they all sort of make the same remark. And one thing I found interesting about some of the early commentary is that they all, or several of them, seem to be interested in this question of whether mathematical theorems have some sort of pre-existence before their discovery, or this question of the necessity of mathematical truths. And so they all of these mathematicians, they all seem to take the position that mathematical theorems are pre-existent, that when you prove a theorem, like as a human being who does mathematics, you're just discovering something that had existence prior to that discovery. And the reason I think this is interesting is because that question of the pre-existence of a mathematical theorem is not really what Cavailles and Lotman were talking about. That wasn't really the question for them. But as soon as the mathematicians sort of, I think, like as soon as they start hearing the idea of philosophy of mathematics, then they sort of immediately gravitate towards this question for whatever reason. And it's also interesting that there are no mathematicians present at this meeting, or who at least who comment at this meeting, who take a constructivist position, for example, who think that mathematical theorems are human constructions and are the result of some sort of human activity, and therefore that they don't pre-exist their discovery or creation. So this is definitely a minority position within mathematics, but it's not like it's not a position that is completely excluded from mathematics. There are mathematicians who have a constructivist philosophy of mathematics, and so it might have been interesting to see what someone from that perspective would have made of some of these ideas as well. And then so the people that have commented so far have made a few objections. So there's this question of the necessity of mathematical discovery. So it's a slightly different question than the question of the pre-existence of mathematical theorems, but the question is whether the creation of, or the discovery of, a certain mathematical concept or mathematical proposition at a certain time was necessary. And so you can take sort of two different positions on this. So you could say that there's a contingency to mathematical discovery, in the sense that what ended up being discovered or produced at a certain time could very well have not been discovered or produced at that time. Just if someone had gotten hit by a bus the day before they proved this theorem, then maybe that theorem would never have been proven. The other position would be that there's a necessity, in the sense that if that person had not proven that theorem, then someone else would have done it in the next year, or in 5 years, or whatever time period. And so some of the objections that are made in this commentary period have to do with this question of the necessity of discoveries in mathematics. Yeah, so maybe we can stop there and then pick up from where we ended last time. We weren't 100% sure where we stopped last time because we missed a week, so our memories are not that clear on the point of where exactly we ended, but we're on page 16 as far as my notes indicate, so I apologize if we repeat something that we looked at last time, but I'll pick up from page 16, which is about halfway through Preexistence contribution or comment on the the discussion. So I'll read the rest of his comment, and then we can pause there. So starting from page 16. One could cite many other examples. In elementary geometry, one introduces the consideration of supplementary trihedra. Here again, I don't think there's a real phenomenon that forces us to consider these supplementary trihedra, but it does provide a convenient way to transform one proposition into another in elementary geometry. I see, therefore, in the examples I have just mentioned, two categories of notions, some that fall well within the framework of an autonomous mathematics, and others, on the contrary, that do not seem to me to be reconcilable with the idea of an autonomy of mathematics. On the contrary, this leads me to agree with Mr. Cavailles, for reasons different from his own, it is true, on the unpredictability of mathematics, placing myself at a point of view which, moreover, is entirely reconcilable with that presented by Mr. Paul Lévy, and which would seem to lead to a contrary conclusion. Mr. Lévy gave many examples where problems could not fail to be solved by mathematicians, and in this sense, mathematics was predictable, because these were problems that mathematicians had posed for the internal development of mathematics. But there are constantly, in the development of sciences outside mathematics, problems that arise that are imposed on mathematicians that mathematicians are asked to solve and that give them new ideas, forcing them to introduce new notions. And those ones are unpredictable. We do not know, we cannot even imagine the nature of the problems that in 50 years' time, technology or physics may pose to mathematicians. Perhaps we will have the means to solve these problems by drawing on the existing arsenal of mathematical theories. Perhaps we will have to create new mathematical tools. There is an impulse from outside and whose interventions are of an unpredictable nature. That is what I wanted to say about autonomy and non-predictability of mathematics. In the footnote here, these are footnotes added by Fréchet to the stenography afterwards. So he says, I developed these 2 points, among others, in a report presented in Zurich in December 1938 on the question of the foundations of mathematics and general analysis at a colloquium organized by the International Institute for Intellectual Cooperation, whose debates will be published by that institute. End of the footnote. As for Mr. Lotman's thesis, I am a little hesitant to comment on most of it because I find different possible interpretations. Some seem to me to be quite immediate and acceptable, but do not seem to me to be reconcilable with the conclusion. This is probably due to what I did not quite understand. I see at the beginning sentences like this. The establishment of effective mathematical relations seems to me, in fact, to be rationally subsequent to the problem of the possibility of such bonds in general. Mr. Lotman was, moreover, careful to point out that, for him, this is not a historical point of view. Indeed, from the historical point of view, the answer is not doubtful. The establishment of effective mathematical relations is, on the contrary, certainly anterior to the problem of the possibility of such bonds. So what exactly does it mean, rationally posterior? I ask the same question for the sentence. We see in what sense we can speak of the participation of distinct mathematical theories in a common dialectic that dominates them. Considering these two sentences in the text that surrounds them, it seems to me that there is an answer that would come quite naturally. It is that the different mathematical theories, especially the proofs contained in these theories, consist of reasonings applied to certain particular circumstances, but that they all belong to the same general theory, which Mr. Lotman designates, I believe, under the name of theory of ideas, and the mathematicians would probably call logic. If that were the case, I think everyone would agree, but it would be so obvious that I do not think Mr. Lotman meant that precisely. In any case, it would be irreconcilable with the end of his presentation. Mathematical thought, therefore, has the eminent role of offering the philosopher the constantly repeated spectacle of the genesis of the real from the idea. I do not know exactly what this means, but from the reflections I made earlier, it seems to me that it is the real that gave rise to the idea, at least as far as mathematics is concerned. It is the demands of reality that have posed mathematical problems, that have led mathematicians to use logic and to formulate certain definitions, certain axioms. I can see, therefore, the genesis of the idea from the real, but I confess that I do not understand the opposite position. Perhaps the rest of the discussion will clarify this point. And another footnote from Fréchet. While correcting the stenography of my speech, I note that the main difficulty for me was indeed to understand Mr. Lotman's language precisely and accurately. As he indicated in his reply, what he means by the real does not in any way correspond to the concrete, the sensible, with which I had identified the real. In the absence of this identification, my objection can be dropped, but it was not useless to give once again a precise example of the importance of a univocal interpretation of the language used. I have been told by philosophers that this difficulty, which appears more clearly in a debate between philosophers and mathematicians, is not absent from discussions where only philosophers by profession meet. Right, so here we have, again, discussion of the autonomy thesis, so this thesis that mathematics has a certain necessity in its development, that its notions appear not as a matter of just contingent historical accident, but there's a necessity of the appearance of a notion at a particular time. And Preexistence here, he says he doesn't necessarily want to reject the notion of autonomy, but he wants to present something distinct from autonomy, an alternate sort of mode of development within mathematics, and he points to the way that mathematics draws from other disciplines, or is solicited by other disciplines, so that physics, for example, will have a particular problem, and there will be a problem of physics that requires the formulation of some new mathematical notion, because of this role of physics in soliciting something from mathematics, there's not this autonomy that, or at least for Preexistence, he doesn't think this we can characterize this as autonomy, because there's this role of an external discipline in bringing about this the new mathematical notion. And then his commentary on Lotman, as he notes in his footnote there, he in particular he tends to look at the relationship between the real and the ideal in Lotman as a relationship between something physical or sensible, and then something supersensible, which is not quite how Lotman understands the distinction between the real and the ideal. So in Lotman's presentation, and then in his response at the end that we'll get to later today, he characterizes this relationship between the ideal and the real as one that takes place between the realm of ideas, this dialectical relationship between notions, the realm of ideas on the one hand, and then the realm of concrete mathematical theories on the other. So when he talks about the genesis of the real from the ideal, he's talking about how concrete mathematical theories are produced out of the dialectic of opposed notions, and he makes a brief comment about redoing the Timaeus, which suggests a role of his account of dialectics in sort of laying the foundations for physics, that would be, in some sense, similar to the way that for Plato you have, in the Timaeus, you have these mathematical principles that govern the creation of the universe. But that's a separate step in mathematical philosophy for Lotman. It's not the same thing as the passage from the dialectical notions to the concrete mathematical theories. There's another step from there to the physical world. And then he also, Preexistence here also, he seems to have difficulty with this notion of what is rationally anterior and rationally posterior, which I don't think is a necessarily very difficult notion. And it's one that you can find in mathematics itself, or not sort of explicitly stated in mathematics, but you have, if you compare the presentation of a mathematical subject in a textbook compared to the way that the same content was presented when it was first introduced, you can see that in the textbook written 50, 100 years later, it's presented in a very different way than the way the material was presented when it was first introduced. So the historical, you have a historical relationship of anteriority between different mathematical notions. So one notion is introduced before another one in time, but then you can also look at within a given presentation, you can look at the order of presentation of the notions and say that this notion is presented first and then serves as the basis for the next notion. And I don't think that's an especially obscure relation. Right, and then so Angus has a question. Is this Lotman's point about how the question may not be explicitly formulated before the solution is determined? Yeah, so he brings us up in his response at the end. So yes, so you can have a question that is only understood in a vague way or some sort of obscure way. And then it's only once you solve that problem or answer that question that you have a way of formulating the question clearly. And so the actual formulation of the question might only happen after or at the same time as the solution is found. And so there's a sort of this sort of groping in the dark, I guess you can say, of just sort of trial and error of trying to find these solutions to problems that are not fully understood. And then it's only once you actually solve the problem that you fully understand what the problem was in the first place. And so even though, so despite all that, despite the historical reality of the question only being formulated after the solution is found, there's still a sense in which the question is logically anterior to the problem, to the solution, or to the answer. Like if you're writing a textbook after the solution has been found, you're going to state the problem first, and then you explain what the solution is. Yeah, this notion of rational anteriority, I don't think is necessarily something mysterious. It's just a question of what sort of comes first in a presentation, in when you have a clear understanding of the subject, as opposed to what happened to come first in historical development, which might not necessarily be the most fundamental principles once you have a clear presentation of that subject. Okay, so let's go on to the next intervention from Erasman. I'm not sure how long this one is. Yeah, it's about a page, so we can just read that one in one go. If someone else would like to read.
I can read. Mr. Erasman. I have noted some thoughts that relate to Mr. Lotman's thesis. It seems to me extremely interesting to see in it the general problems that we find in several mathematical theories. But I quote one of the most characteristic sentences. Quote, one of the essential theses of this work affirms the need to separate the supramathematical conception of the problem of the bonds that certain notions support between them and the mathematical discovery of these effective bonds within a theory. If I have understood correctly, it would not be possible in this field of supramathematical dialectics to specify and study the nature of these relations between general ideas. The philosopher could only highlight the urgency of the problem. It seems to me that if we want to talk about these general ideas, We already conceive in a vague way the existence of certain general relations between these ideas. Therefore, we cannot stop halfway. We must set ourselves the truly mathematical problem of explicitly formulating these general relationships between the ideas considered. I believe this problem can be satisfactorily resolved as far as are concerned relations between the whole and its parts, the global and the local, the intrinsic and the extrinsic, etc. Thus, the relations between a fundamental set and its parts form precisely the subject of a chapter of abstract set theory. Between the parts of a set, we have the following relations: inclusion of one part in another, intersection of two parts, union of two parts, complementary part of a part. In the set of parts of a fundamental set, these relations give rise to a whole calculation, namely Boolean algebra. These are a few general relationships that can be found in any mathematical theory. Given a fundamental set equipped with a particular mathematical structure, for example, a group structure or a topological space structure, the relationship between this fundamental set and one of its parts results in the mathematical notion of structure induced on the part. I cannot be more precise because we would first have to define the general concept of mathematical structure. The problem of the relations between intrinsic and extrinsic properties and the problem of the situational properties of a part in a fundamental set is nothing other than the problem of the relations between the structure of a fundamental set and the structures induced on a part and on the complementary part. With regard to the notions of local and global, it seems to me that the notion of local has meaning only for a structure of a topological space, as we then have the notion of neighborhood of a point. The notion of local property at a point can be deduced from the notion of structure induced on an arbitrary neighborhood of the point. We come once again to a purely mathematical concept. There are many more examples. I think that the general problems raised by Mr. Lotman can be expressed in mathematical terms, and this is in line with the thought expressed in the summary of Mr. Cavailles' thesis. Talking about mathematics can only be redoing it.
Right, so here, to some extent, I think Lotman is sort of agreeing with Lotman without realizing it, because Lotman says precisely that mathematical theories are essential for the working out of the dialectic of the notions. So the notions are related to each other in various ways. But as soon as you try to actually work out what that relation is, you're immediately doing mathematics. So in philosophy, you can pose the problem of the relationship between the whole and the part, but you can only actually produce a solution to that problem by doing mathematics and having a mathematical theory of wholes and parts, like in the example that Lotman gives, where we have the relationships between parts in set theory, which produces a Boolean algebra structure. So I don't think Lotman is really disagreeing with Lotman here, or what he takes to be an objection to Lotman is really just what Lotman was saying. So it's not really an objection, or it shouldn't really be taken as an objection. Okay, so we can go on to Hippolyte's next intervention. Let's see how long this is. Yeah, it's just over a page, so I can read this one. Oh, and maybe just before I start, I'll just mention that Hippolyte is the first of the people commenting here who is a philosopher rather than a mathematician. So that's something to keep in mind as we go through it. Okay, Mr. Hippolyte. I must confess that although I fully understood Mr. Cavailles' thesis, I understood Mr. Lotman's argument much less well. What struck me in Mr. Lotman's presentation was the ambiguity of the word dialectic, and the different meanings with which this word has been used. It seems to me that, applied to mathematics, the word dialectic was used in three different senses, or at least I thought I discerned three quite different meanings of the term. With the first meaning of the term, Mr. Lotman would agree with the thesis of Cavailles. Their two conceptions on this point would be similar. Dialectic would be the very experience of the life of mathematics. It would reconcile in a way a need for development that has already been mentioned and the apparent contingency of this development. In another meaning, Mr. Lotman's dialectic is a kind of problematic, in the modern sense of the word, something completely different. I believe that it is above all in this sense, moreover, that he uses the word. This dialectic is a problematic, a kind of opening on theoretical problems that the mathematician would come to embody in his research. And in a third meaning, and this is precisely where the ambiguity seems to me to be strongest, Mr. Lotman takes up the word dialectic with the meaning with which philosophers have taken it most often. It is indeed a question of dialectic, of form and matter, local and global, etc. It seems to me, for my part, that if we wanted at all costs to use the word dialectic in the philosophy of mathematics, we would have to use it only in the first sense, that is to say, in the sense of a life of mathematical experience over the course of its history. I will take an example that has struck me quite strongly. It is the development of the theory of equations from Viette to Galois. I think that if there is a necessity, as Mr. Cartan said, in the development of mathematics, this necessity appears very clearly in the development of this theory from Viette to Descartes, but it no longer appears at all when it comes to the discoveries of Galois. It seems that there is, in mathematical theory, something quite new, something unexpected, that has been introduced and that cannot exactly be foreseen from the previous development of mathematics. This is something that struck me quite strongly, studying the decomposition of a group into invariant subgroups in Galois, and the application of this problem to the algebraic solution of equations after studying the problem of the theory of algebraic equations in Descartes. It seems to me that in this case we can both see a necessary development and then the appearance of a completely new method in the problem, an unpredictable creation, if not after the fact. There is another remark that this problem of the evolution of the theory of equations from Viette to Galois inspires in me. One could express the matter vulgarly by saying that we do not know how to undo what we know how to do, or that intellectual activity exceeds itself in what it generates. The given equations seem enigmatic mathematical beings in a way. We know how to build them by the products of binomials, as Harriot did. We can thus manage to construct equations of any degree, but then we are unable, the problem of division after that of multiplication, to undo any given equation. It was necessary to attempt this analysis in general to introduce new notions which, moreover, let themselves be understood in a certain way. Thus, for example, the imaginaries foreseen by Descartes. Descartes in 1637 explicitly said that there were n positive, negative, or imaginary roots of the equation of the nth degree. This is a prediction of what appeared much later. I think, in summary, that I would rather agree with Mr. Cavailles, who wants to see in mathematics an essential independent life. One might also think that the necessity of the development of mathematics and historical contingency must be reconciled in this life of mathematics. As for Mr. Lotman's thesis, one might fear by adopting it to see mathematical notions evaporate in a certain way into pure theoretical problems that go beyond them, such as form and matter, the local and the global. The very originality of this mathematics would be in danger of disappearing. I did not quite understand in Mr. Lotman's thesis whether the mathematician ended up finding these problems or whether it was on the contrary, and this would be the problematic, an ideal requirement of these problems, which, given first, would then come to be embodied in mathematics. There is an ambiguity here, but perhaps I have misunderstood Mr. Lotman's thesis. Right, so here Hippolyte suggests that there are three different meanings to the notion of dialectic or the term dialectic that Lotman uses in his presentation. So the first is where dialectic would just mean the experience of mathematics or the development of mathematics through history. And he takes this notion of dialectics to be unproblematic, and he thinks this is the correct notion of dialectics, or the use of the term dialectics that should be preserved in philosophy of mathematics. And then a second meaning is where dialectic would mean a problematic, so a set of problems, or a framework in which certain problems appear. And in Lotman's presentation, in Lotman's response later on, he accepts this meaning of the word as being a valid one, and he argues that these first two meanings are actually reconcilable with each other, and are not actually contradictory. And then the third meaning is the use of the term dialectic as the relationship between notions like form and matter, local and global, and so on. And Lotman will specify in his response later on that this third notion should not be taken to be something independent. So there's no such thing as a dialectic that would be independent from mathematics. That would be something extra mathematical. It's only in mathematics itself that this dialectic realizes itself. The relationship between notions is only brought about in concrete mathematical theories. And then after this question about the meaning of the word dialectic, he introduces the discussion of the development of algebra, and he suggests that there's both a necessity and a contingency in that history, in different moments of that history. So you have a necessary development through part of the history, and then with Galois you have this moment of contingency or of the introduction of something that was not at all foreseen or foreseeable in what was present before. And so here, for Hippolyte, the development of mathematics would not be something that is both necessary and contingent at the same time, but it's something that would be alternately necessary and contingent. So you would have certain moments of necessity and other moments of contingency. And so this is a notion of mathematical development that is not a dialectical one in the way that Cavailles' notion of mathematical development is dialectical. And then the last bit is an objection to Lotman again, where he argues that by accepting the idea of something like a supramathematical dialectic that is realized in mathematics, you are sort of subordinating mathematics to something non-mathematical, and this is something that sort of erases the specificity of mathematics. It makes mathematics into something that is sort of secondary to the understanding of the dialectic of the ideas themselves, and so I think for Lotman, the way that he would answer this objection is that it's not that mathematics is secondary. It's just that the actual work of mathematics always has to do with concrete mathematical theories, and it's only afterwards that the philosopher can come and find the work of the dialectical ideas in that the concrete mathematical theory. So with respect to our knowledge, the actual work of the mathematician comes first, even if rationally speaking or logically speaking, the dialectical ideas are primary, and the concrete mathematical theory is something that is secondary in the logical sense. So there's no there isn't exactly a subordination of mathematicians to philosophers, for example. Uh, it's actually the other way around in terms of the um, historical introduction of these ideas, or how we come to grasp dialectical ideas in the first place.
I'm a little bit confused about this, the point about the third sense of dialectic. The idea that the ideal notions and ideas are not independent of mathematics. So my understanding was that they were kind of pre-mathematical and not mathematical. I guess maybe is the point just that they're only made concrete in terms of mathematical theories.
Yeah, I think that's right. So yes, they're pre-mathematical in the sense that they are logically anterior to mathematics, so that um, once we have a rational grasp of a mathematical theory, we can see the dialectical ideas at work in that theory. So we can see a certain theory as having to do with the relationship between intrinsic and extrinsic, for example. But it's only ever in concrete mathematical theories that the relationship between these dialectical notions actually works itself out, or is sort of incarnated, so that the problem of the relationship between the intrinsic and the extrinsic is not something that can be worked out independently of mathematics. It's only by doing mathematics that we can actually have a solution to the problem of how the intrinsic and the extrinsic are related to each other.
Okay, thanks. That makes sense.
Right. But yeah, it's a subtle position because on the one hand, he wants to recognize this pre-mathematical reality that mathematics incarnates, and then on the other hand, he wants to say that this pre-mathematical reality is only ever instantiated in concrete mathematical theories. So the relationship between the pre-mathematical reality, the dialectical ideas, and the actual mathematical reality is a subtle one. It's not straightforward. Okay, so let's go on to Schrecker's discussion, which is a short one. Yeah, let's go on to Schrecker's discussion. If someone else would like to read.
I can read it. Should I just read the Cavailles response and then Schrecker's response to Cavailles?
Yeah, you can, like, Cavailles just makes a little interjection, and you can continue past that point.
Okay. Mr. Schrecker, after so many mathematical considerations, it may be allowed to a philosopher to present some reflections that do not absolutely respect the autonomy in which mathematicians necessarily confine themselves. Their target is the impossibility affirmed by Mr. Cavailles of defining mathematics. According to him, any definition of mathematics would lead to absurdity, because it would be impossible to define mathematics by something that it is not. But it seems to me that this same difficulty is found in all sciences. No science is capable of being defined by its own means and methods. It is always necessary to put oneself outside of science to be able to arrive at a definition of its field. But that doesn't mean that we would necessarily define mathematics by something it is not. Mathematics is a science. This is the first element of a definition, and it is certainly not heteronymous. It is a hypothetico-deductive science. That is a second element. But it is true that we cannot define it while remaining in the mathematical formalism and while respecting, in the definition, the autonomy of the mathematical field. Formalism and autonomy apply to all mathematical problems. However, the definition of mathematics is not itself a mathematical problem. It is a problem that arises in the theory of science, which is in no way obliged to fit into the coherence of mathematical formalism itself. Thus, the refutation of the hypothetico-deductive character of mathematics seems to me to be turning in a circle, because this refutation itself uses the hypothetico-deductive method. An attempt is made to give this refutation by means of reasoning which, being deductive, is necessarily also hypothetical, because it presupposes the effectiveness of the formalism by which it operates. By denying the hypothetico-deductive character of mathematics, one turns in a closed circle or in a closed system that has neither entry nor exit. And then Cavailles interjects and says, I have never denied this character. I have only said that one cannot define it by this alone because we must use mathematical theory. Strecker responds, but it is obvious that if we try to define mathematics by using mathematical theories, we will never succeed. If, on the contrary, one decides to define them by other means, by emancipating oneself from formalism and employing historical or philosophical methods, it seems possible to succeed. And all the more so because, without a doubt, we know how to distinguish mathematics from other sciences when we undertake its history or when we consider it as an object of philosophy. Some great mathematicians have proposed a definition which, although it is not absolutely satisfactory, nevertheless seems to me to be on the right track. Thus, Bolzano defined mathematics as the science of general laws that all possible things necessarily follow. And H. Weil proposed a definition that does not differ from this essentially. It does not seem, therefore, that the philosopher is obliged, in the face of the problem of the definition of mathematics, to the resignation that Mr. Cavailles asks of him.
Right. So this has to do with the question that Cavailles raised, or the objection that Cavailles raised to the attempt to define mathematics. And he suggests that, or he argues that it's not possible to define mathematics because you either have to say that mathematics is X, which is something not mathematical, and then you're defining it in terms of something that it is not. Or on the other hand, you use mathematics itself to define mathematics. So you use some sort of mathematical method to define mathematics, but then you're sort of going in a circle, and you never enter into that circle and produce a definition that could sort of serve as an explanation of what mathematics is. And Schrecker here, he argues that we can in fact give a definition of mathematics, but we have to do so using non-mathematical methods, so historical or philosophical methods. And so he gives not a definition of mathematics, but what he calls an element of the definition. So the notion of mathematics as a hypothetical deductive science. And Cavailles, in his interjection here, he explains that he doesn't deny that mathematics has this property of being a hypothetical deductive science. So, namely, a science that proceeds by making hypotheses and then deducing consequences of those hypotheses. So Cavailles doesn't deny that mathematics has this property, but he denies that this property can be defined independently of mathematics, because once you say that mathematics is a hypothetical deductive system, or a hypothetical deductive science, then you have to explain what you mean by something deductive, or what a deduction is, and then you are sort of inevitably led to construct a theory of deduction, which is precisely mathematical logic. So your definition of mathematics as a hypothetical deductive science relies on mathematical logic as a discipline, a subdiscipline of mathematics, and so you're not actually sort of producing an entry into mathematics. You're actually just presupposing the existence of mathematics, and sort of stuck in that circle. So I think the next bit after the objection is probably more relevant, where Schrecker he points to the definition that Bolzano had presented, that mathematics is the science of general laws that all possible things necessarily follow. And this definition is not 100% clear, because again, we can ask what it means for something to be like, what is a possible thing, or what does it mean for laws to be necessary? And then if we want to make these notions clear, we will end up bringing back in mathematical logic again. But it seems, at least to sort of advance the work of trying to explain what mathematics is. I think there's something right about this definition of mathematics as the science of the laws that all things follow. But it's definitely not sufficient as a definition, and Cavailles points to this in his response a little bit later, where he says that if someone had no idea what mathematics was, and you said it's the science of all the laws that all possible things necessarily follow, then that doesn't really give an idea of what mathematics is to that person. So there's again, your definition fails at introducing someone into the circle of mathematics. Okay, so let's go on to the next bit. There are two short interventions, so I'll read both of those together. So the first one is given in indirect speech for whatever reason, rather than verbatim. So Mr. Chabotti returns to Mr. Carton's remark that the dialectical themes envisaged by Mr. Lotman are found only in certain parts of modern mathematics. There are few examples of this in the work of the set theorists. When one has actually recognized one of these themes in certain operations of mathematics, it would perhaps be interesting to see what initial conditions, what axioms imposed on the sets considered, allow this common character of the theories considered. Mr. Dubray, I was particularly interested in what Mr. Cavailles said about the effort that mathematicians make to reflect on their own science, and about one of the difficulties they then encountered. To study the non-contradiction of a system of axioms, it is necessary to involve mathematical theories that are of a higher level. For example, to establish the non-contradiction of arithmetic, transfinite induction is used. I wonder whether this difficulty is not more apparent than real, and whether the power of the means necessary to establish the non-contradiction of a system of axioms does not rather highlight the deep nature and true scope of these axioms. Let us take the example of integers. It is perhaps not excessive to say that if we want to exhaust the mathematical content of this notion, we are led to link it to that of a well-ordered set. Let us indeed focus our attention not on the natural numbers considered individually, but on the set of these numbers. This set is ordered and even well-ordered. In addition, each element admits an antecedent. Since the notions of set, order, well-ordering, and antecedent are logically independent of that of natural number, let us consider a priori well-ordered sets where each element admits an antecedent. Two possibilities arise depending on whether or not the set admits a last element. We will call it finite in the first case, countable in the second. Starting from these definitions, it is easy to see that any two countable sets have the same power, and that every finite set has the same power as a certain segment of a countable set. The set of natural numbers thus appears as a countable set chosen once and for all, but arbitrary, to the segments of which one compares the finite sets. From the notions of union and product of sets arise immediately, with their properties, the operations on the natural numbers. It is seen that a small number of remarkable properties characterize finite sets and countable sets, in particular the set of natural numbers, in the more general class of well-ordered sets. We have also highlighted a fact that, if you think about it, seems quite natural. Like so many other sets considered in algebra, the set of integers is actually defined only up to isomorphism. So here we have a question about the difficulty that Cavailles presented in the negative portion of his presentation. So the fact that in order to establish the non-contradiction of arithmetic, you have to use mathematical theories that are more powerful than arithmetic, like in Gensen's proof of the non-contradiction, where he has to use transfinite induction. And so here Dubreuil takes it that what this shows is not that there's something inherently impossible about foundations in mathematics, but rather that this result shows that the axioms in question, the axioms of number theory, for example, or of arithmetic, have some sort of depth to them that hasn't been exhausted yet. And he suggests an alternate approach, which would start from the notion of a well-ordered set rather than starting from the notion of natural numbers. And here, so maybe I'll just explain what well-ordering means. And I think I might have mentioned this last time, but this notion of well-ordering is something that was introduced by Zermelo, who gave a proof that every set can be well-ordered, which was a controversial proof because some people objected to his use of the axiom of choice, and it was only when he or some people objected to the method of proof, and then he gave an axiomatization of set theory, where he explicitly states the axiom of choice, and that developed into a whole controversy about that axiom. But so well-ordering means that, so a set is well-ordered if every subset of that set has a least element. So a set of natural numbers, for example, if you take a set of natural numbers, then every subset of that set has a least element, a smallest number. Whereas if you take the set of real numbers, for example, I'm mixing that up. But there are other sets that are not well ordered necessarily. So you have to actually show that you can well order them. But it's not immediately obvious that if you take a subset of a given set, that it can be well ordered. It's something that you have to actually prove. So then Dubreuil takes it that if you start from this notion of well-ordered sets, and then you define the natural numbers to be just an isomorphism class of well-ordered sets with no last member, then you can avoid some of these difficulties. And I think I don't know all the technical details, but I think this doesn't exactly work. I think you do need to use principles like transfinite induction that are more powerful than principles of arithmetic in order to prove the consistency of arithmetic. So you can definitely construct the natural numbers out of set theory, for example. Like this is done in like a first or second year logic class today. So you can define the 0 as the empty set, and then 1 is the set that contains the empty set and the singleton of the empty set, and then and so on. So you can define natural numbers just in terms of sets, but to actually prove that this the set of the theory of arithmetic is non-contradictory, you have to use notions like transfinite induction. Maybe I'll just mention or explain a little bit what he says right at the end when he says that the set of integers is defined only up to isomorphism. So isomorphism is in sort of vague terms, it just means that two things are isomorphic if they have the same structure in some relevant sense of structure. So in in group theory, then two groups are isomorphic if they have the same group structure, or in category theory, two categories are isomorphic if they have the same category structure, etc. And in various particular theories, there are different ways of showing that two things are isomorphic. And so it depends on the particular type of structure in question, what exactly that isomorphism means. But in general, you can show that something is isomorphic by showing that a function between those two things has an inverse. So you can go from A to B using some function f, and then you can go from B back to A using the inverse of f, and you get back the A that you started with. So in the case where you have a function that has an inverse, then you have an isomorphism between the two sets or the two structures that are being related to each other by that function. And then so to say that something is defined only up to isomorphism means that you define the structure of something, but you're considering isomorphic structures to be equivalent or interchangeable in some way. So, like if you take the sets of numbers, the set of natural numbers, for example, the set of natural numbers is isomorphic to the set of even numbers because you can take any number and multiply it by 2 and you get an even number. And so in some sense those two sets are equivalent to each other if you're just taking them as sets. There's no you're essentially just labeling the elements in a different way. You're not actually the two sets have the same structure. And so that's what defining something up to isomorphism means. It's treating isomorphic structures as equivalent, as just variants of each other rather than as distinct structures. Okay, so let's go on to the next bit. So Cavailles' response is a couple of pages long. So maybe we can read a page or so and then stop. Angus, if you'd like to read.
Yeah. Are we at I shall reply?
Yes.
Okay. Mr. Cavailles, I shall reply, if you don't mind, in the reverse order of the speeches. To Dupre, I will answer in a very simple way. Dupre is not the only one to say that what Gödel discovered must inevitably have been found. Yes, but when Gödel presented his paper, no one suspected that such a thing was possible. One worked around Hilbert von Neumann, whom I have mentioned. One worked for years to try to demonstrate with finite means the non-contradiction of arithmetic, without appealing to transfinite induction. Von Neumann himself was very surprised by Gödel's result. As for the priority between notions of integers and well-ordered or countable sets, it is a question for the mathematician. I will not allow myself to solve it myself. My humble opinion is that the notion of integer is the first one, and this seems to me also confirmed by the work, for example, of von Neumann on the axiomatization of set theory, where prior to the notion of a well-ordered set, there is what he calls the notion of numbering. That is to say, an extension of the notion of integer by matching an object each time with the system of already numbered objects. By extending in this way, we arrive at the notion of transfinite number. This has only a very vague connection with Gödel's result. The aim was to demonstrate whether it was possible using finite arithmetic, the ordinary complete induction axiom, and not the general complete induction, to make appear a certain property in the symbols, arithmetical non-contradiction. Gödel managed to demonstrate that this was impossible. This is a considerable result. About a month ago, Gödel introduced another considerable result: the possibility of demonstrating, using the axioms of set theory without the axiom of choice, the non-contradiction with these axioms of the axiom of choice, and even of the continuum hypothesis. If I cite this new example, it is to show that the expansion of these meta-mathematical procedures makes it possible to ensure, if we give ourselves radically new procedures, increasingly vast theories. For Schrecker, I do not know if he is satisfied with his definition of mathematics. We should ask mathematicians what they think of it. If someone has never done mathematics and they are told it is a deductive science, I do not think it will give them the idea of mathematics. What I mean is this: what do we actually think, or what do we actually think of when we talk about science and deductive science? There is only one way to think something deductively, and that is to do mathematics. Here I touch a little on the problem that I wanted to avoid, and you will tell me that the definition of a deductive science is a logical question. I do not want to get into this debate, but if we want to know what a deduction is, we have only one way: to do mathematics, and the so-called deductive logical procedures are a very elementary mathematical combinatorics. I would add that this is very important. I can rely on the testimony of Carnap, who was in favor of reducing any mathematical notion to a logical notion. However, he had to specify in his, I can't pronounce that, logisch syntax der Sprache, I guess, that now he was saying the meaning of a sign is its mode of use. It is impossible to give full meaning to the notion of deduction independently of mathematical development. Moreover, if you limit yourself by deduction to the propositional or the predicate calculus, you will not have the axiom of complete induction, and it will not mean anything to say mathematics is a deductive science, since the axiom of complete induction, as Poincaré said, as Hilbert took it up again, is the very essence of mathematical life. Should I stop there?
Yeah, let's stop there. Let's see. Yeah, so he Cavailles here talks about Gödel's incompleteness theorems, I should say, which we've talked about before, and he mentions how surprising these theorems were when they were first presented, even if afterwards you can sort of you can see the necessity of them. And actually, I've just been reading. There's a biography of Gödel that came out last year that I've been reading, and he talks about how von Neumann was working on a proof of the consistency of arithmetic, and he says that he had a dream on two successive nights. He had a dream of how to solve the problem, how to solve how to prove the consistency of arithmetic, and each time he woke up and then ran to his desk and tried to write down as much as possible, but he didn't get there, and he got a little bit further, but he didn't actually solve the problem because, of course, we now know it was unsolvable. But he always regretted that he didn't have the same dream on the third night because he thinks he would have solved it. But that's just to show that before Gödel presented his results, everyone sort of assumed that it would be possible to prove the consistency of arithmetic using finite methods, and it was just a matter of finding the actual methods that would work. And so Gödel's result was very surprising, and there were mathematicians who were very upset by this result, and I forget who it was in particular. There was someone who refused to speak to Gödel at some conference afterwards, because he was upset about this result. And then Cavailles also here mentions the non-contradiction proof that Gödel gives later on. This is in 1939, so it's just prior to the talk itself. So Gödel gives a proof that the axioms of set theory, if you take the axioms of set theory without the axiom of choice, then you can't make them contradictory by adding the axiom of choice. So if you assume that the axioms of set theory are not contradictory, then adding the axiom of choice doesn't make them contradictory. And then likewise for the continuum hypothesis. And the continuum hypothesis is we probably shouldn't get into it here, but it's a hypothesis that Cantor stated about the sizes of infinite sets and which sizes are possible. And Cantor tried to prove it for years, but was never able to do so. And Gödel eventually showed. Gödel showed that it was non-contradictory. So if you take the axioms of set theory, you don't get a contradiction by adding the continuum hypothesis as a new axiom. So you also don't get a contradiction if you add the negation of the continuum hypothesis as an axiom. So that means it's not possible to prove the continuum hypothesis just from the axioms of set theory. So what Cantor was trying to do was actually impossible. So that's what that example or that reference to the Gödel's non-contradiction proofs here is about. And Cavailles takes this as an instance of how metamathematics or the mathematization of what was a philosophical problem leads to the expansion of mathematics. And this is related to the impossibility of defining mathematics, because if you say that mathematics is defined by these given set of procedures or these 10 or 100 or whatever deductive procedures, then the next year or 10 years later or whatever, someone else is going to invent a new procedure that is not on your list, and this procedure will still be mathematical, but it's a novel introduction. It's not something you could foresee in advance. And then he responds to Schrecker about this question of defining mathematics, and then he suggests that this is not a very satisfactory definition, as we've talked about earlier. Defining mathematics in terms of deduction is not satisfactory because in order to understand what deduction means, you have to actually do mathematics. So you're not actually you're still sort of caught in the circle of mathematics. You're not standing outside and then defining what that circle is. And then he points to so in Carnap. So Carnap is at that time at least was a logicist. So he thought that the notions of mathematics should be reduced to notions of logic. But then at the same time, he has to say that the meaning of a sign is its mode of use, so that it's only in the actual development of a mathematical theory in which the sign appears that you can actually explain how what the meaning of that sign is. And then he mentions, so if you try to limit deduction and say that deduction just means deduction in the propositional calculus or the predicate calculus or whatever logical system you pick, then you don't have these extra logical principles that are essential for mathematics, like the principle of complete induction. So without these principles, it's impossible to do mathematics as it's in its full development. In even basic stuff like arithmetic is not possible. So again, this shows that you can't define mathematics in terms of something that is not mathematical. You have to actually, the only way to explain what mathematics is, or to do math, the only way to show what mathematics is actually to do mathematics. You can't define it in terms of something else outside of mathematics. Okay, so let's go on to the next part of the discussion. So I can read this bit. With what Mr. Fréchet has said to me, I regret that I completely disagree. I'm not trying to define mathematics, but by means of mathematics, to know what it means to know, to think. It is basically very modestly taken up the problem posed by Kant. Mathematical knowledge is central to knowing what knowledge is. Mr. Fréchet says to me, there are notions that are taken from the real world and other notions that are added by the mathematician. I answered that I don't understand what it means because I don't know what knowing the real world is other than to do mathematics on the real world. What do you call the real world? I'm not an idealist. I believe in what is experienced. J'ai vécu. To think of a plane, do you live it? What do I think when I say I think this room? Either I will speak of lived impressions, d'impressions vécues, rigorously untranslatable, rigorously unusable by means of a ruler, or I will do the geometry of this room and I will do mathematics. What do you think when you think of plane? The geometrical properties of this plane, the symmetry? Our disagreement stems from the fact that I have not expressed my thoughts enough. I feel all my inadequacy. I spoke of a solidarity based on sensible gestures. There is not on the one hand a sensible world that would be given, and on the other hand the world of the mathematician outside. The symmetry of the plane, for example, coincides with this character of permutation, which is one of the properties that I experience in the sensible world. Mr. Fréchet, this character is revealed to me by the sensible world. Mr. Cavailles, Hilbert used to say that there is never any mathematical thought without the use of signs, without sensible work on signs. I apologize for saying this. I suppose that mathematicians agree with me that they experiment on the signs they have. There is, in a formula, a kind of call. Who could do without the circle with its center, the cross of coordinate axes? Arithmetic signs are written figures, geometric figures are drawn formulas, and it would be as impossible for a mathematician to do without them as it would be to ignore the parentheses when writing. I quote from memory Hilbert's very nice article on this. Before the war, it is from the early Hilbert. This article studies unconscious experiments on possible relationships, the possible use of certain signs. I note the use I can make of them. There is a possibility of experimentation. We cannot exhaustively define the mathematical object independently of the implementation of the object in the sensible world. I believe that this starting point is never left, in the sense that there is an internal solidarity, and that whenever we substitute more thought-out objects for a less thought-out mathematical object, that is to say, when we separate what was simply accidentally united by the procedure that I have indicated, to that extent, all the same, we are not leaving the sensible world. But there is autonomy. Indeed, one, the questions posed by direct practice in its unification, theoretical physics, take on meaning and form only by transforming themselves into mathematical questions, that is, by inserting itself into the becoming of pure mathematics. Two, this insertion does not cause a break. Physics acts only as an occasional revelator. In reality, the problem was latent, internal difficulties, the requirement to overcome a system of notions that are too sketchy, in the fabric of the mathematical substance. Here again, I can invoke history. A close enough study would always show for all the examples of services rendered by physics to mathematics that there is an internal necessity, that physics is only an occasion. I think it is essential if you want to understand, and on this it seems to me that the disagreement is complete, but this has at least one advantage, which is that we can decide. Of course, we will not do it here. I think it is essential to see, in the notions used by the mathematician to solve problems, the result of a requirement that was already in the previous system. It is possible, because the mathematician is lazy or for extrinsic reasons, that he does not solve certain problems, that he cohabits with difficulties. But I do not believe that we can, because of this, deny the role of internal necessity. Let's stop here. So here we have, I think this is a very interesting passage, because here we have, I guess, the epistemological consequences of this notion of Cavailles' understanding of mathematics. And so he suggests here that what he's trying to do is not to define mathematics, and ultimately it's not a question of mathematics in its own terms or for its own sake that he's investigating. He's investigating mathematics as the sort of paradigm instance of human knowledge. So he wants to know what it is to know something, and he takes mathematics to be the key notion of, or the key instance of knowledge. And so he says, when we talk about knowing the real world, then the only true content of that knowledge is a mathematical content. So if we just talk about sensible experience, then it's something that is not exactly knowledge in the proper sense of the word. It's only when we start applying mathematics to the sensible world that we have knowledge in the proper sense of the word. And then he talks about the relationship between the sensible and the mathematical, and he's made this he's introduced this notion of a gesture before in his presentation, and here he talks about the continuity, or the immanence, we can say, of mathematics in the sensible world. So when you do mathematics, you actually write signs on a piece of paper or on a blackboard or whatever. You actually are doing something in the sensible world, and you have a system of gestures that are considered to be allowed, and you have sets of rules for what you can do with certain signs, and the types of gestures that you're allowed to do, given certain signs already present. And so there's a certain sense in which mathematics is an experimental science, in the sense that you have to actually write down certain expressions on the paper or on the blackboard, and then you see what happens. In a sense, you try out different gestures that you are allowed to do, and then you find that certain gestures have a consequence that allows you to proceed further, and other ones sort of end up in a dead end. And then, so by trial and error, you and then maybe flashes of insight, you sort of end up discovering the solution to a problem. And so there's this contingency in advance to the problem, in the sense that I said, there's this trial and error aspect of solving a problem, and then it's only after the problem is solved that the necessity of that solution becomes apparent. But at the same time, we have to keep both the necessity and the contingency in mind when we're talking about mathematical dialectics. And then he goes on to talk about what Fréchet had objected in connection with physics and other sciences presenting problems to mathematics, and he makes a pretty strong claim here. He claims that these problems that are set for mathematics by other sciences are only ever occasions for mathematics' own development, so that there's really no sort of external influence on mathematics. So whenever physics or some other discipline sets a problem for mathematics, you're really only just eliciting something that was already implicit in the state of mathematics, and in principle, mathematicians could have arrived at the notions that they in the actual history they arrived at only through influence of physics. In principle, they could have reached those notions just through the internal development of mathematics. And I think this strong thesis of autonomy is probably hard to maintain. I think there are definitely instances of mathematical theories that were first motivated by problems from physics, and it's only afterwards that the connection of that mathematical theory with other theories and the sort of internal development of mathematics is made. Okay, so let's go on to the next sort of round. Let's see, there's Lévy. Yeah, we can finish. We can go up to the beginning of Lotman's response. Angus, if you want to read the next bit.
Yeah, this is starting with Lévy's response to Cavailles in 23.
I think we were, just the line before that, it seems to me.
Okay. I'll just reread that line. It seems to me that Mr. Paul Lévy was making more or less the same objection to me. And Lévy says, I wanted to express the idea that there was something existing a priori, regardless of how one discovers it. Cavailles, here again, I have expressed myself in an insufficient way. I am not saying at all that these notions are dependent on a historical order. I believe they are required by the problems. When we have used integers, it is obvious that we will posit the product as commutative. There will be other cases where we use non-commutative products. Therefore, when you say, given a problem, there is a solution, or look, you will find it, as Hilbert said, this is what I indicated as the projection of a system of mathematical gestures. The historical mathematician, contingent, may stop, be tired, but the requirement of a problem imposes the gesture that will solve it. This is, if you like, what I had indicated when I said that it is the reality of knowledge, which from the very point of view of an anthropology or philosophy of the human constitution is the extraordinary miracle of human destiny, independent of life in the lived world, the monde vécu. There are problems that require solutions and lead away from what is by a necessary sequence. Here I would not be very far from Lotman, except for the word real, which bothers me. It would be a question of distinguishing whether it is the real sensible, and here I do not agree, or if it is the actual reality of beings, and here I agree with him. And perhaps also with Mr. Paul Lévy. That is to say, the solution is obviously required by the problem that has been raised. You say that it is somewhere, it is a matter of taste. Levy responds, the word somewhere indicates that it is not localized. Frichet, personally, I completely agree with Mr. Paul Levy. I see this proposition as existing outside us. Cavailles says, Lotman separates himself from me. What I find very interesting in what he does are the bonds that he makes appear between certain theories. The future will show us who is right. Personally, I am very reluctant to posit something else that would dominate the actual thinking of the mathematician. I see a requirement in the problems themselves. Perhaps this is what he calls the dialectic that dominates. Otherwise, I believe that through this dialectic, we only arrive at very general relations, or relations such as those indicated by Mr. Cartan. There is undoubtedly interest in looking in this area, but to turn this into a philosophical position does not seem possible to me. I think we talked about this last time, but this seems like a pretty clear statement of the difference between Cavailles and Lotman. Just that Lotman has the pre-mathematical ideal problematic, out of which mathematical theories are made concrete. And for Cavailles, the development, it goes from problem to solution, and the solution is contained in the problem and not in an ideal realm.
Yeah, I think that's right. I think this is sort of the core of the difference between them is this notion that mathematics is governed by something extra mathematical that Lotman has. But I also think that here we see sort of where they come closest to each other as well, because this notion that Cavailles points to here, this idea that there's a necessity or a requirement in the problems themselves, in the development of mathematics. As he says here, he says maybe this is what Lotman calls the dialectic that dominates. So this necessity within the problems um, is where Cavailles's notion of the dialectic and Lotman's, I think, come closest to each other, and then they sort of diverge when Lotman takes the dialectic to be an incarnation of something super mathematical. So I think that last paragraph is really a key one to understand both the difference between them and also where they come closest to each other. Okay, so let's go on to the next section. I think let's see, it's about a little bit more than a page, so I'll just read the rest. Lotman's response, and then we can discuss. We started a little bit later today, so we still have some time. Mr. Lotman, I would first of all like to thank Mr. Cartan for the kindness with which he justified the logical interpretation I have given of certain contemporary mathematical theories, among which some of the most beautiful emanate from him. I am also grateful to him for admitting that notions such as local and global, matter and form are not linked to a given theory, but can be found in very different theories, such as analysis or geometry. In short, if Mr. Cartan does not feel for himself the need for a reference to a dialectic, he recognizes the right of philosophers to do so, and no encouragement could be more precious to them. I will be much less in agreement with Mr. Fréchet. I spoke of the genesis of the real from the idea. Mr. Fréchet says that he understands only the opposite, that is to say, the genesis of the idea from the real, by abstraction, of course. It seems to me in this respect that a distinction must be made between the historical order of human reflection and the logical or ontological order of dependence of notions. Mathematical theories seem to me to be given their full meaning when interpreted as answers to a dialectical problem or a question. It is clear that it is only through an effort of regressive analysis that one goes back from theory to the idea it embodies. But it is no less true that it is of the nature of an answer to be an answer to a logically prior question, even if the awareness of the question is later than the knowledge of the answer. The genesis I have spoken of is therefore transcendental and not empirical, to use Kant's vocabulary. As far as Mr. Ehresmann's objections are concerned, I am convinced that I agree with him, although he does not want to acknowledge it. Mr. Ehresmann says to me that the problems that I call dialectical remain vague until I specify the statement, and at that point they become pure mathematical problems. I have myself written that dialectics, not being affirmative of any effective situation and being a pure problematic, necessarily extended itself into actual mathematical theories. The question is whether it is possible to consider the statement of a logical or metaphysical problem independently of any concrete mathematical solution. The answer to this question is in the history of philosophy. Let me give just two examples. One is that of the Leibnizian monad. It is possible to conceive as inscribed in the internal properties of a being all the relations that it supports with the whole universe. Is it possible to conceive as inscribed in the internal properties of a being all the relations that it supports with the whole universe? This conception of the monad is purely metaphysical, and I have shown, I believe, in my thesis, the links that unite it with the current theories of analysis cetus, which are, moreover, likewise of Leibnizian inspiration. As a second example, I take the one I gave above, the problem of reciprocity of action between two or more bodies. Problem certainly distinct from Newtonian theory, and of which Kant nevertheless believed that he had found the definitive solution in the famous law of universal attraction. The history of philosophy thus shows the autonomy of the conception of structural problems in relation to the contingent elaboration of particular mathematical solutions. Mr. Cavailles points out to me that I have attached great importance to theorems which establish the existence of certain functions on certain surfaces or certain sets, but that this result may seem less surprising if one realizes that the sets in question have been rigged so that it is quickly possible to find on them the functions sought. It would therefore seem that we find on a set only what we put beforehand. Such a way of presenting things does not seem to me to sufficiently highlight the fact that there can be two kinds of rigging in the sense of Mr. Cavailles, those which are fruitful and those which are not. A set never possesses, in the matter of properties, any others than those given to it a priori by axioms, but it turns out that some of these artificial definitions have the consequence of bringing a set or a surface to such a state of completion or perfection that this internal perfection flourishes in affirmations of the existence of new functions defined on this set. This fecundity of certain structural properties, which extends itself into a genesis of new mathematical beings, seems to me precisely to distinguish within the possibilities of axiomatic definition creative conceptions from those that lead to nothing truly new. Mr. Hippolyte reproaches me for using the term dialectic in at least three different meanings. There is one that I do not accept. It is the one according to which there could exist a dialectic of the local and the global that would be sufficient in itself independently of mathematics. On the other hand, the other two ways seem to me to complement each other and not to destroy each other. Mathematics constitutes a true dialectic of the local and the global, of rest and movement, in the sense that dialectic studies the way in which one can compose between them the abstract notions in question. This does not prevent us from conceiving a dialectic prior to mathematics, conceived as problematic. Mr. Hippolyte tells me that to pose a problem is to conceive nothing. I reply after Heidegger that it is already delimiting the field of the existent. Mr. Schrecker mainly addressed Mr. Cavailles, but I believe that we agree in admitting the legitimacy of a theory of abstract structures, independent of the objects linked together by these structures. It only remains for me to reply to Mr. Cavailles. The precise point of our disagreement is not about the nature of mathematical experience, l'expérience mathématique, but about its meaning and scope. That this experience is the sine qua non of mathematical thought, that is certain, but I believe that we must find in experience something other than experience. It is necessary to grasp, beyond the temporal circumstances of the discovery, the ideal reality which is the only one capable of giving its meaning and value to mathematical experience. I conceive of this ideal reality as independent of the activity of the mind, which in my opinion intervenes only when it comes to creating actual mathematics. Mathematics belongs to the field of action, but the dialectic is above all a universe to contemplate, whose admirable spectacle justifies and rewards the long efforts of the mind. Right, so here we have Lotman's responses to some of the objections that have been raised to his arguments by the various participants. And so he, in relation to Fréchet, he rejects the idea of the genesis of the ideal from the real by abstraction. And he says in the historical order of human reflection, so in the order in which the ideas, the various mathematical concepts first appear, you might have something like an ordering from the real to the ideal, and then something like abstraction. So we come to know we come to have the concept of numbers possibly by abstracting from real objects and defining this numerical property that objects have. But in the logical or ontological order, it's numbers that are more fundamental or that are anterior to concrete objects or physical objects, and the idea in the specific sense that Lotman uses it in the sense of a dialectical idea is anterior to mathematical concepts, and this is an anteriority in a logical or ontological sense, so it's something more fundamental, and then the mathematical theory that is actually realizing that dialectical idea is something that is derived from the underlying realm of the ideas. And then, as I mentioned when we were talking about Erasman's comments, his objections are effectively just restating Lotmans Thesis that it's only in mathematical theories that the relations between dialectical notions are realized. So you can state the problem in philosophers can state the problems of the relationship between dialectical notions, but only mathematicians can actually solve them by creating mathematical theories. And then, I'll skip ahead to Hippolyte, the response to Hippolyte. So here he rejects the third notion of dialectic that Hippolyte had suggested was at work in Lotman's presentation. So that he denies that there is such a thing as a dialectic of the local and the global, and the intrinsic and the extrinsic and so on, that would be independent of mathematics. So it's only in mathematical theories that these notions are related to each other. In trying to solve the problem of what that relation is, you end up having to do mathematics. You can't solve it through philosophical thought. And then the last bit is Lotman's response to Cavailles, and he says that they agree with each other on the notion on the nature of mathematical experience, but they disagree about the meaning and scope of mathematical experience. So they both regard mathematical experience as being something dialectical, and as we saw at the end of Cavailles' presentation, they sort of approach each other on the understanding of what that dialectic consists in, but then they diverge in that Lotman sees this mathematical experience as grasping something that is beyond that experience, this ideal reality, this realm of the dialectic, and then he gives a very Platonic depiction of what this means, and so he talks about contemplating the universe of the dialectic as the reward for the the efforts of the mind in doing mathematics. So this is, again, a very Platonic notion, not in the sense that Platonism is usually understood in philosophy of mathematics, but in relation to Plato's work itself. Okay, so I think we can end here unless there's any final thoughts or questions or comments. Okay. Thanks. Thanks for reading through this with me. We can. So for next week, maybe we can go back to Simondon and start on the second volume, which consists of several texts that are related to the individuation book itself, like the actual thesis. So there's the first one is called History of the Notion of the Individual, and it's essentially like a history of philosophy from the perspective of the notion of the individual. So he starts with the pre-Socratics and goes through Plato and Aristotle, and he does a little bit of medieval philosophy. And there's a strangely long section on Rousseau. It's like 20 pages or something like that. So that will take the text itself is like 150 pages or something like that. So it'll take us a while to get through that. And then there are a couple of other texts that fill out the rest of the volume. So it'll take us, a few months to get through the second volume. I think it's shorter than the first volume, though.
Is there as much quantum physics in the second volume?
No, I don't think so. I think we're pretty safe from quantum physics.
That's exciting to me.
I liked the quantum physics stuff in volume 1, but I know it was kind of difficult. I've been actually doing a fair amount of reading in that area, in philosophy of physics and stuff like that over the past few months, as a sort of sparked by our discussions in reading Simondon.
Oh, nice. Yeah, I definitely left it behind when we finished part 1 of the individuation.
Yeah, okay. So thanks again, and hopefully see you all next week. We'll pick up with Simondon again.
Sounds good. Thanks.
All right, bye.